He was born into a small house on a cold January morning. The village lay flat and quiet. Fields spread out like a simple map. The baby's name was Isaac Newton. People around him saw only another child. No one guessed the shape his life would take. As a boy, Isaac watched the world more than he spoke. He liked to sit by the stream and watch small ripples move and meet. He liked to take toys apart and see the tiny parts inside. While other children ran and shouted, he stayed near a gate, looking at ropes and wheels and how they pulled and turned. School was not always for him. He did not love noisy rooms and crowds. He loved a book and a quiet corner. His mother wanted him to be a farmer for a while. She thought the farm would make him steady and give him work. Isaac tried the farm. The work felt heavy and the life felt wrong. His fingers wanted to hold a pen more than a spade. So he returned to study. Cambridge opened a new world for him. Dusty book rooms, long lists of names, and drawings of the sky filled his days. He read about earlier thinkers who looked at stars in motion. He liked mathematics because it spoke plainly and never lied. Numbers and proofs felt like a clear language. Then the plague came and the college closed. People left town and quiet filled the rooms. Isaac returned to his mother's cottage with time and little to do. Some people waste empty days in such quiet. Isaac used the quiet for thought. He built small machines, rolled balls down slopes, and timed them with simple devices. He wrote notes. He tested again and again. One afternoon, an apple fell from a tree. The story is small, but the thought was large. Isaac did not stop at seeing the apple fall. He asked, why does it fall straight down and not to the side? He asked, could the same pole that brings apples down also keep the moon moving around the earth? The questions sounded bold, but he kept asking them. He loved simple experiments. He built wooden ramps and watched how spheres rolled. He used flowing water to measure time. He measured and wrote precise notes. The notes grew into pages, and the pages grew into a habit of working. Try, record, test, revise. That habit would become a model others copied. Light also caught his attention. He let a thin beam of sunlight pass through a glass prism. The light fell on a white wall in a small rain of colors. He saw that white light was not single. It contained many colors mixed together. A simple prism and a patch of sun taught him a deep secret about light. People remember the apple and the prism not because he shouted ideas, but because he listened and he tested. He sat still until the world became sensible. He loved small details and small experiments. He believed that gentle attention to small things could make large laws. When the college reopened, Isaac returned with new notes and odd tools. He had the quiet habit of careful testing and a mind ready to translate small events into general rules. The apple and the garden and the prism's color were small scenes that began a long way of thinking. He had started to shape ideas that would reach far beyond his village. Cambridge gave him more than books. It gave a language. Mathematics became his daily tool. He learned to turn motion into numbers, to write a sentence about speed and another about direction, and to join them in rules. He noticed that many motions followed simple patterns. A thrown stone, a rolling cart, and the moon all moved in ways that could be understood if you had the right rules. He liked rules that worked everywhere. He wanted a few strong ideas that explained many events. While he worked, he thought about change. How does speed change when a force pushes? How does a path curve under a steady pull? He created a new language for these questions. That work later took the form of calculus, a way to describe how things change and how small changes add up. The method was new and not easy to see, but it let him tie ideas about motion together. Isaac used sharp experiments and clear drawings. He rolled balls down slopes to see how time and distance related. He measured carefully. He showed that a gentle slope made a ball speed up slowly, and a steep slope made it speed up fast. He wrote the rules down with numbers and words. The practice of turning a simple test into a clear rule was central to his work. He read the work of earlier thinkers and built on it. Galileo had shown that many bodies fall in similar ways. Kepler had collected careful observations of planets. Newton used those ideas and put them together. Where others saw separate facts, he looked for one rule that explained them all. Letters and meetings with other thinkers sharpened his thoughts. He often worked quietly and then wrote long, careful papers. He liked to show the steps so others could follow. This patience with detail made his work strong and hard to argue with. In a world before calculators, Isaac used simple machines and his own mind as tools. He took a problem, broke it into small parts, and solved each part with numbers and reason. The result was a way of thinking that could predict motion. The same ideas could describe a cart, a cannonball, and the path of a planet. When some leaders in science asked for proof that a single force might explain falling objects and planetary motion, he answered with a clear book. He wrote the rules that later people called Newton's laws. These laws felt simple. Objects move in straight lines unless a force acts. Change of motion depends on force and mass, and actions have equal reactions. Though simple, these rules carried a wide reach. His math did not remain hidden in pages. It moved into machines and into ships and into the building of structures. Sailors and engineers could use simple formulas to plan voyages and build better machines. The language of numbers helped turn invention into reliable craft. Even when disputes rose over credit for ideas, over methods, over words, his habit of precise notes and careful proof held strong. He did not shout, he wrote. That way of work helped others verify, repeat, and build upon his ideas. His gift was not only deep thought, but a clear method for sharing that thought. The apple story is a tidy image. It shows a man in a garden, thinking. The actual work took long nights and many small tests. He did not only see fruit fall, he measured, thought, and then wrote a law that spoke plainly. He proposed that every object pulls on every other object. The strength of the pull depends on their masses and the distance between them. Closer objects pull harder. More massive objects pull harder. This simple rule explained the motion of an apple and the path of the moon. Once he had such a rule, many things followed. He showed why planets follow predictable paths, why comets appear at times, and why the tides happen when the moon pulls on Earth. Engineers used the rule to aim cannons and design machines. Astronomers used it to calculate where planets would be next week or next year. His 3 laws of motion fit together with gravity. The first law said objects keep moving unless a force acts. The second law gave a simple formula to calculate how speed changes with force. The third law showed that forces come in pairs. When you push, something pushes back. These ideas felt new but natural. They looked like common sense, framed in numbers. The power came from the combination: simple wording, clear mathematics, and the habit of testing with the eye and the ruler. He made the world feel less like a place of separate mysteries and more like a place run by rules. Given the initial conditions, positions, and velocities, you could, in principle, calculate the future. That new confidence changed how people planned, built, and explored. Even with the new rules, the work required patience. He tested many cases and showed how the rules applied to each. He used step-by-step diagrams and careful proofs so that the rules would stand up to discussion and experiment. Critics had less room to object when the math was clear and the experiments repeatable. The apple in the garden became a symbol. Small things can lead to large laws. Little questions can open a path to greater understanding. He showed that the same simple truth could connect a child's falling fruit to the flight of the moon. Something pushes back. Light was another field where his quiet experiments spoke loudly. He took a beam of sunlight and sent it through a small glass prism. On the wall, a band of color appeared. He moved a second prism and combined the colors back into white light. That simple trick showed that white light contained hidden colors, not that the glass made colors. He tested lenses and mirrors and thought about how eyes see. Early telescopes used curved lenses but suffered from color problems. Newton tried a different idea: use mirrors to focus light instead of lenses. He built a reflecting telescope with a curved mirror that sent clear images to an eyepiece. The design reduced defects and made clearer views of the sky possible. His work on optics was both practical and curious. He asked how light moved and how colors formed. He proposed that light might be made of small particles, which he called corpuscles. That view matched some experiments and helped explain bright, sharp rays. Later work would show that light also has wave-like behavior, and scientists would reconcile both views. Still, his careful experiments and new instruments pushed the study of light forward. The telescope he built allowed better images of stars and planets. Astronomers could see fainter objects and measure positions more accurately. The instrument showed how experiments and clever design could change what people could observe and so change what they could know. He wrote long notes, repeated tests, and drew diagrams so others could build similar instruments. His work in optics meant that future scientists could ask new questions about the nature of light and the design of tools to look at the sky. He was a solitary man in many ways. He worked long hours and kept careful notes. He liked a quiet room and patience in experiments. He did not marry or have children, and he gave much of his time to study. Yet he took public roles later in life. He led the Royal Society and served as Master of the Mint. In the Mint, he worked to improve coin quality and fight counterfeiters.
He turned the same careful thought he used in science to matters of public duty. People came to respect his honesty and his clear mind. He had rivals and he had fights. Scientific life then was not always gentle. He argued sharply with other thinkers. The disputes could become personal. Yet these fierce debates also forced clearer thinking and better experiments. The pressure of argument sharpened the science. He loved books and collected them. He liked to study old texts and new observations. He wrote letters to other scientists and welcomed a lively exchange of ideas. He could be direct and sometimes harsh, but he also respected careful work. Young thinkers came to study with him and to learn how to write clearly and test carefully.
Religion was part of his inner life. He believed nature had order and that a creator had set the laws in place. This belief did not slow his experiments. It gave him a reason to look for simple, elegant rules. He thought that discovering nature's order was a way to see a deeper design. Even when fame grew, his habit of patient testing stayed. He repeated experiments, recorded each step, and left notes that others could read. That method made his work reliable and useful. It also taught a lesson for the next centuries. Careful work and clear writing matter as much as bright discovery. Later in life, honors came. He became president of the Royal Society and was knighted. People called him Sir Isaac Newton. He moved to London and took on public roles. Yet, even with public life, he kept returning to his desk and his lab. When he died, he left a stack of notes, books, and proofs. He left a book, the Principia, which guided science for generations. The rules he wrote in that book shaped how people built machines, sailed ships, and studied the sky. Engineers used the laws to craft bridges and machines. Sailors used them to predict motion and to plan journeys. Astronomers used them for the positions of planets. His legacy is not only in theorems, but in a way of working. He built a habit that combined small experiments, careful measurements, clear mathematics, and step-by-step explanation. That model became the core of modern science. Test, measure, calculate, and publish. Later scientists built on his work and sometimes changed the view. In the 20th century, new ideas like relativity and quantum physics showed limits to his laws in extreme conditions. Still, for most everyday problems and many engineering tasks, his rules remain the right tools. Planes, cars, and bridges still follow ideas born in his notebooks. For listeners, there are small lessons in his life. Pay attention to small things. A falling apple or a prism of light can start a life of discovery. Keep careful notes. Try again when experiments fail. Look for simple rules that explain many things. Debate and test ideas rather than accept them without proof. He showed that a quiet life of attention can change how millions see the world. From a small cottage to a seat in the Royal Society, his path was not noisy. It was steady, careful, and full of questions. If you walk in a garden and watch an apple drop or hold a glass prism in sun, you may find the same starting point he had, a small question that opens a very wide door.